Today, we are going to talk about the most alone places in the universe, worlds that drift through endless darkness, without a star to warm them, without a sky that ever sees sunrise, without anything above them but the cold silence of interstellar space. We are going to talk about rogue planets, and we are going to ask a question that, until very recently, most scientists would have dismissed as pure fantasy. Could something be alive out there? Not alive in the way we imagine alien life. Not creatures looking up at foreign stars, not civilizations sending signals across the cosmos, but alive in the quiet, stubborn, microscopic way that life insists on existing even in the most hostile corners of our own world. Alive the way bacteria thrive in Antarctic ice. The way organisms cluster around hydrothermal vents at the bottom of the ocean where no sunlight has ever reached. Alive simply because the conditions allow it. That is what we are here to explore tonight. But before we can ask whether life is possible on these worlds, we need to understand what they are. We need to understand how a planet, something that begins its existence as part of the solar system, something that forms in the warmth and chaos of a young star's orbit, ends up completely alone, cast out, wandering, a cosmic orphan with no sun, no system, and no destination. That story, it turns out, is one of the most dramatic in all of astronomy. Let us start with something that might seem obvious, but rarely gets acknowledged directly. The universe does not care about order. We tend to think of planetary systems as stable, permanent arrangements. The sun in the center, the planets in their lanes, everything moving in predictable ellipses, as it has for billions of years. And for our solar system, that picture is mostly accurate today. But it was not always. And for many other systems across the galaxy, that kind of stability never arrived at all. The early life of a planetary system is violent. When a star forms from a collapsing cloud of gas and dust, the leftover material spreads into a rotating disk around it. Within that disk, dust grains collide and stick together, growing slowly into pebbles, then rocks, then planetesimals, bodies large enough for gravity to take over. Over millions of years, these planetesimals merge and grow into planets. But the process is not clean. It is not orderly. Multiple large bodies are competing for the same space, pulling on each other gravitationally, nudging each other's orbits in ways that compound over time. In many systems, this gravitational competition ends badly for at least one planet. Two large bodies can fall into what astronomers call resonance, a situation where their orbital periods line up in a simple ratio, causing them to pull on each other at regular, repeated intervals. Over time, those repeated pulls can amplify, pushing one body into an increasingly unstable orbit. A close encounter between two massive planets can result in a gravitational slingshot, one planet gaining energy from the interaction and being hurled outward at tremendous speed, while the other falls inward. A passing star, making a close approach to a young solar system, can disrupt the orbits of outer planets entirely. And in systems with multiple large gas giants jostling for position, the odds of at least one ejection are, according to current models, quite high. The planet that gets ejected does not simply slow down and stop. It carries the velocity of that gravitational interaction with it, moving away from its home star at speeds that can reach hundreds of kilometers per second. The star's gravity weakens with distance. Past a certain point, the planet is moving too fast for gravity to pull it back. It crosses an invisible threshold and enters interstellar space. And from that moment, it is free, unchained, and utterly, permanently alone. This is how most rogue planets are thought to form, according to the current scientific consensus. The ejection model is the most widely supported explanation, but it is worth noting that it is not the only one. Some researchers propose that a fraction of rogue planets, particularly the larger, gas giant-sized ones, may never have been part of the solar system at all. They may have formed directly from the collapse of a small gas cloud, the same way stars form, but without enough mass to ignite nuclear fusion. These objects blur the boundary between planets and the smallest type of failed star, known as a brown dwarf. The distinction matters scientifically, but for our purposes tonight, the result is the same: a world drifting alone in the dark, A third formation pathway, less commonly discussed but not dismissed, involves stellar remnants. When a massive star reaches the end of its life and explodes as a supernova, the shock wave can disrupt any planetary system orbiting it, sending planets flying in all directions. Research published in late 2025 specifically examined this scenario, finding that planets ejected by supernova explosions can retain their moons under certain conditions, a detail we will return to later, because it turns out to matter enormously for the question of life. So we have a sense of how these worlds end up alone. But how many of them are there? The answer, even by the conservative estimates of modern astronomy, is staggering. For decades, rogue planets were theoretical objects. Astronomers suspected they should exist. The physics of planetary formation all but demanded it, but actually finding one is extraordinarily difficult. A planet that orbits a star can be detected in several ways: by the slight dimming it causes when it passes in front of its star, by the gravitational wobble it induces in its star's motion, by the infrared light it reflects. A rogue planet, by definition, has no star. It emits almost no light of its own. Against the blackness of interstellar space, it is nearly invisible. The technique that is proven most useful for finding them is called gravitational microlensing. The principle comes directly from Einstein's general theory of relativity, which describes how mass curves the fabric of space-time. When a massive object passes between Earth and a more distant star, its gravity acts like a lens, bending the light from that background star and briefly making it appear brighter. If the object doing the lensing is a planet with no star, that brightening event, lasting anywhere from a few hours to a few days, is one of the only signals it leaves behind. Because rogue planets have no stellar parent to transit across, gravitational microlensing has become the most successful method for detecting them. The events are extraordinarily rare from any given line of sight, which means the only way to find them in meaningful numbers is to watch enormous numbers of stars simultaneously, waiting for the galaxy's drifting population of orphan worlds to pass in front of them one by one. Ground-based surveys have been doing exactly this for years. The microlensing observations in Astrophysics Survey, known as MOA, operated from New Zealand and monitored millions of stars toward the center of the Milky Way, where stellar density is highest and microlensing events most frequent. The Korea Microlensing Telescope Network, KMTNet, runs 3 telescopes on 3 different continents simultaneously, allowing near-continuous monitoring of the same fields. These surveys have produced a growing but still small collection of confirmed or candidate rogue planets, fewer than 10 low-mass detections by the most rigorous count. But from even that small sample, the statistical implications are enormous. Some research suggests that untethered worlds in our galaxy may be around 6 times more common than planets orbiting parent stars. Other estimates are even higher. Current models suggest our galaxy may contain as many as a quadrillion rogue planets. That is a 1 followed by 15 zeros. Even the more conservative estimates place the number in the billions or trillions. The precise figure is genuinely unknown, and scientists are honest about that uncertainty. What is not seriously disputed is the basic conclusion: rogue planets are not rare anomalies. They may be among the most common planetary objects in the galaxy. The instrument that is expected to move this question from extrapolation toward an actual census is NASA's Nancy Grace Roman Space Telescope, now targeted for launch no earlier than September 2026. Roman will run a dedicated microlensing survey from space, staring at fields near the galactic center for months at a time, free from the atmospheric blurring that limits ground-based telescopes. Previous estimates suggested Roman would find around 50 Earth-mass rogue planets during its mission. More recent modeling raises that number to approximately 400, and those 400 would represent only the ones Roman is sensitive enough to detect, not the full population. Even more significantly, in January 2026, a team led by astronomer Su Dong achieved something that had never been done before. By observing a microlensing event simultaneously from Earth and from space using ESA's Gaia telescope, researchers obtained the first direct measurement of a rogue planet's mass. Not a rough statistical estimate, but an actual measurement. The object, located roughly 10,000 light-years away in the direction of the galactic center, turned out to have a mass comparable to Saturn. The finding, published in the journal Science, strengthened the case that the galaxy is filled with castaway worlds born within solar systems and later violently expelled. This is where the science stands right now. In 2026, we have confirmed that rogue planets exist. We have measured the mass of one directly for first time. We suspect they are extraordinarily common, and we are building the instruments that will, within the next few years, begin to reveal their true numbers. Before we move on, there is one more discovery worth pausing on, because it changes the story in an unexpected way. In late 2025, using the European Southern Observatory's Very Large Telescope in Chile, a team of astronomers turned their attention to a young rogue planet in a constellation called Chameleon, roughly 620 light-years from Earth. The object, named CHA 1107 to 7626, is a young planetary mass body drifting without a star, but it is not simply floating passively through space. It is actively feeding, drawing material from a surrounding disk of gas and dust at a rate that astonished the researchers who measured it. By August 2025, the planet was accumulating material approximately 8 times faster than just a few months earlier, at a rate of 6 billion tons per second. The most powerful episode of accretion ever recorded for an object of this kind. What makes this discovery philosophically interesting, not just scientifically, is what it implies about identity. We think of rogue planets as finished objects, fully formed worlds that have been cast out of their systems and are now simply drifting inert, unchanging. But CHA 1107 to 7626 is still becoming. It is still growing. It formed without a star. It is feeding without a star, and it is doing so through a process, magnetic activity triggering sudden mass influx, that had previously only been observed in young stars. The boundary between a planet and a star, it turns out, is blurrier than we thought. And the life story of a rogue planet is more complex than the simple narrative of ejection and abandonment. Let us take a moment to sit with the scale of what we are describing. The Milky Way is approximately 100,000 light-years across. Light, traveling at 299,792 kilometers per second, the fastest speed physically possible, takes 100,000 years to cross it. The nearest star to our sun, Proxima Centauri, is 4.24 light-years away. At the speed of the fastest spacecraft humanity has ever built, the Voyager probes, that distance would take roughly 73,000 years to cover. Interstellar space, the space between stars, is not empty, but it is extraordinarily sparse. A cubic centimeter of interstellar space contains, on average, roughly 1 atom. Compare that to the air in this room, which contains approximately 27 million trillion atoms per cubic centimeter. The void between stars is, for most practical purposes, as close to nothing as anything in the known universe gets. And through this void, rogue planets drift. They do not drift quickly by cosmic standards. Most move at velocities of tens to hundreds of kilometers per second relative to nearby stars, fast enough to cross the distance between Earth and the Moon in a matter of hours, but still only a tiny fraction of the speed of light. At these speeds, a rogue planet might cross the full width of the galaxy in a few billion years. Some have been doing exactly that, wandering, for longer than the Earth has existed. Think about what that means. There are worlds out there, some of them roughly the size of Earth, some larger, some smaller, that have been traveling through interstellar darkness for 3, 4, perhaps 5 billion years. They formed around a star we will never identify, in a system we can never reconstruct. They were expelled, perhaps by a collision, perhaps by a gravitational interaction, perhaps by their star going supernova, and since that moment, they have moved in a straight line to the void, passing through no system, orbiting nothing, approaching nothing close enough to be captured. No sunrise, no seasons, no tide from a moon's gravity or a star's pull. Just a faint, ancient light of distant stars. Stars so far away they are mere points, providing no warmth, casting no shadows. The cosmic microwave background radiation, the afterglow of the Big Bang itself, washing over the surface at a temperature of 2.7 degrees above absolute zero. These worlds are not dramatic in any cinematic sense. They are quiet. They are dark. They are, by any intuitive measure, dead. And yet, here's where the story takes its turn. For most of the history of astronomy, when scientists imagine what a rogue planet must be like, they imagine exactly that picture. A frozen, inert rock, or a gas giant with no atmosphere we're speaking of, slowly radiating away whatever heat was born within the surrounding void. A dead world. End of story. That picture began to change seriously in 1999, when a scientist named David Stephenson published a paper that asked a different kind of question. Stephenson, a planetary scientist at Caltech, pointed out something that seems obvious in retrospect, but had been largely overlooked. A planet does not need a star to stay warm. A planet has its own internal heat sources. And under the right conditions, those heat sources might be enough to maintain liquid water, not on the surface, but beneath it. This was the beginning of what became known informally as the Steppenwolf hypothesis. The name comes from the Hermann Hesse novel, a lone wolf, outside society, surviving on its own terms. Stephenson argued that if a rogue planet possessed an extremely high-pressure hydrogen atmosphere, the pressure broadening of far-infrared absorption by molecular hydrogen could, in combination with the geothermal heat flux alone, support liquid water on the planet's surface, not just beneath the ice, on the surface. This is a hypothesis. It has not been confirmed observationally. No rogue planet has yet been studied in enough detail to verify or refute it, but it is a hypothesis grounded in real physics, published in a peer-reviewed journal, and taken seriously by planetary scientists. It opened a door. And through that door came more ideas, more calculations, more possibilities, all of which we will explore in detail in the next part of our journey tonight. But before we move there, let us return to the philosophical thread. We began by saying that rogue planets are the most alone places in the universe. And in a literal sense, that is true. No star, no system, no neighbors, just a void. But there is another way to think about aloneness. And it is a way that, strangely, connects these wandering worlds to something deeply human. Every rogue planet that was ejected from a solar system was once part of something. It formed in a disk of gas and dust, in the warmth of a young star, surrounded by other forming worlds. It spent perhaps millions of years in that environment, being shaped by gravitational interactions, accumulating mass, developing whatever internal structure it would carry for the rest of its existence. And then, in a cosmically brief moment, it was gone, flung outward, separated from the system that made it. We do not know, of course, whether anything on those worlds experienced that separation. We do not know whether there was ever anything to experience it. But the structure of the event, the formation in community, the violent expulsion, the long solitary journey afterward, carries a weight that is hard to ignore. There is something in the human experience that resonates with it. The idea of being shaped by one environment, then cast into a completely different one. Of carrying the internal structures built in one place into a context where they no longer have the same meaning. Of moving through vast emptiness, still containing whatever heat was there at the beginning, slowly, very slowly, cooling. We are not the rogue planets, but we recognize something in them. Let us close this first part with the state of our knowledge. Cleanly, honestly, without exaggeration, we know that rogue planets exist. We have detected them. We have, for the first time, directly measured the mass of one. We have observed one actively forming, feeding, growing, without a star. We know that they are likely extremely common. Current estimates range from billions to trillions within the Milky Way alone, though the precise number remains unknown and will not be pinned down until telescopes like Roman begin their surveys. We know they form primarily through gravitational ejection from young planetary systems, the most widely accepted mechanism, though direct formation from collapsing gas clouds is also considered possible for larger objects, and supernova-driven ejection has been studied as a third pathway. We know that interstellar space is extraordinarily cold and sparse, and that any rogue planet moving through it loses heat to that environment over geological timescales. And we know, or rather, we have begun to seriously calculate that the cold and the dark may not be the whole story, because inside these worlds, heat persists, physics persists, and where physics permits energy, and where energy meets the right chemistry, the universe is a habit, a quiet, stubborn, remarkable habit of doing something unexpected. That is what Part 2 is about. We left Part 1 with a question hanging in the cold interstellar air. A rogue planet moves through a void where the background temperature hovers just 2.7 degrees above absolute zero. It has no star, no external energy source of any kind. And yet, the physics of its interior, the same physics that operates inside every rocky world in every solar system in the galaxy, continues to function regardless of what surrounds it. Heat does not care whether there is a star nearby. Radioactive decay does not stop because a planet has been ejected. The churning of a molten mantle, the slow compression of rock under its own weight, the friction of tidal forces. None of these processes require sunlight. None of them require a solar system at all. This is the central insight of Part 2. And it is an insight that took longer than it should have to arrive in mainstream planetary science. Perhaps because we are so accustomed to thinking of stars as the origin of all energy, all warmth, all possibility. The sun is so dominant in our experience of what it means for a world to be alive that we build it into our foundational assumptions without fully examining them. Those assumptions, it turns out, are worth examining very carefully. Let's begin with the most fundamental heat source of all, the planet itself. When a rocky planet forms, it does so through a process of accretion, the collision and merging of smaller bodies over millions of years. Those collisions are not gentle. When two planetesimals slam into each other, the kinetic energy of their motion does not simply disappear. It converts, as energy always does, into heat. The larger the colliding bodies, the more energy released. By the time a planet has grown to Earth size, the accumulated heat of all those impacts has, in many models, been sufficient to melt the entire interior, creating what geologists call a magma ocean. That heat does not dissipate quickly. Rock is a poor conductor of heat. The interior of the Earth today, more than 4.5 billion years after formation, is still partially molten. The outer core remains liquid iron and nickel, convecting slowly and generating the magnetic field that protects our surface from the solar wind. The mantle is solid but behaves plastically over geological timescales, flowing in slow convection currents that drive plate tectonics. All of this activity is powered, in part, by heat that was deposited during the violent process of planetary formation billions of years ago. A rogue planet carries the same legacy. If it formed as a rocky world of roughly Earth's mass, it almost certainly went through a similar process of accretion and melting. When it was ejected from its system, whether after a few million years or a few hundred million, it carried that internal heat with it. The ejection itself does not drain the interior. The planet moves through interstellar space, losing heat from its surface to the surrounding void. But the rate at which it loses heat depends on how efficiently the heat can travel from the hot interior to the cold surface. And rock, as we said, is a poor conductor. Depending on the size of the planet, its composition, and how long ago it was ejected, a rogue Earth mass world could retain significant internal heat for billions of years. Not enough to heat the surface to comfortable temperatures. The void is simply too cold, and the surface radiates heat away too efficiently for that. But enough, potentially, to maintain elevated temperatures at depth. The second heat source is, in some ways, even more remarkable: radioactivity. Ordinary rocks, the kind that make up the crust and mantle of Earth-like planets, contain trace amounts of radioactive isotopes. The most important of these for planetary heating are uranium-238, uranium-235, thorium-232, and potassium-40. These isotopes undergo radioactive decay, releasing energy as they do so. The process is slow. That is the nature of isotopes with long half-lives. But it is continuous and extraordinarily reliable. On Earth, Radioactive decay in the mantle is responsible for roughly half of the planet's total heat output. The other half is primordial heat, left over from formation. Together, these two sources drive the geothermal heat flux that maintains the liquid outer core, powers plate tectonics, and creates the volcanic and hydrothermal activity that, as we will discuss shortly, turns out to be deeply relevant to the question of life. A rogue planet made of similar rocky material carries the same radioactive inventory. Uranium, thorium, and potassium do not become less radioactive because a planet has been ejected from its solar system. They continue their slow, steady decay regardless of what is happening outside. The heat they generate continues to flow outward to the mantle and crust toward the surface and eventually into space. The numbers here are worth considering carefully. Uranium 238 has a half-life of approximately 4.47 billion years. Thorium 232 has a half-life of about 14 billion years, longer than the current age of the universe. These are not isotopes that run out on any timescale relevant to planetary habitability. A rogue planet ejected 5 billion years ago, made of Earth-like material, would still be generating radiogenic heat today. Not as much as when it was young. Radioactive decay does diminish over time, but a meaningful, persistent flux. This is not speculation. It is the same physics that keeps Earth geologically active, the same physics that keeps Europa's subsurface ocean liquid, in combination with tidal forces. The same physics that warms the interior of Pluto, a world at the edge of our solar system, where solar heating is negligible, enough to potentially maintain a subsurface ocean. The heat is real. The question for rogue planets is whether it is enough, and whether the planet's structure allows it to be useful rather than simply lost to the void. This is where the atmosphere becomes critical. Imagine an Earth-like rogue planet, ejected from its solar system several billion years ago. Initially, it had an atmosphere, nitrogen, carbon dioxide, water vapor, whatever volatile compounds outgassed from its interior during its warm early period. As the surface cooled, things began to freeze. Water froze first, covering the surface in ice. Carbon dioxide froze next, precipitating out of the atmosphere and forming dry ice deposits. Eventually, even nitrogen, which freezes at 63 Kelvin or roughly minus 210 degrees Celsius, will begin to condense on a cold enough surface. What is left? Mostly hydrogen and helium, the lightest elements, the hardest to freeze, the hardest for a planet's gravity to hold on to over long periods, but the most resistant to condensation in the deep cold of interstellar space. A rocky rogue planet would likely lose much of its hydrogen to space over geological timescales, especially if it lacks a magnetic field to shield its upper atmosphere from energetic particles. But here is where the Steppenwolf hypothesis becomes interesting. A planet that retains even a modest hydrogen-rich atmosphere behaves very differently from one that has lost its atmosphere entirely. Stevenson's 1999 analysis showed that pressure broadening of far-infrared absorption by molecular hydrogen could trap geothermal heat effectively enough to maintain liquid water on the surface, at least in principle and under the right conditions of atmospheric pressure and geothermal flux. The hydrogen atmosphere acts as a blanket, not warmed from outside by starlight, but warmed from below by the planet's own interior. This is a genuine greenhouse effect, but inverted from the way we usually think about it. On Earth, the greenhouse effect traps solar energy that arrives from above. On a Steppenwolf planet, the equivalent effect would trap geothermal energy that arrives from below. The physics of infrared absorption does not distinguish between the two. Whether any real rogue planet has managed to retain such an atmosphere, and whether the geothermal flux of any particular world is sufficient to push surface temperatures above the freezing point of water under that atmospheric blanket, is genuinely unknown. No direct evidence of water or ice has yet been confirmed on any rocky rogue planet, because we have not yet been able to study any of them in sufficient detail. The Steppenwolf scenario remains a hypothesis, a physically grounded, mathematically coherent hypothesis, but a hypothesis nonetheless. What we can say is that the hypothesis cannot be ruled out, And in the search for habitable environments, a hypothesis that cannot be ruled out deserves serious attention. Now, let us go beneath the surface entirely. Even on a world where the surface has long since frozen, where the atmosphere is thinned, where temperatures at the crust have dropped to within a few dozen degrees of absolute zero, the interior remains warmer. The geothermal heat flux, however modest, flows upward, and as it does, it creates a temperature gradient. Warmer at depth, colder near the surface. On a water-rich road planet, this gradient has a specific and important consequence. Water, under sufficient pressure and above a certain temperature, remains liquid. The freezing point of water shifts with pressure. Under the immense pressure of a thick ice layer, it actually decreases slightly, meaning that ice near the base of the ice sheet tends to melt rather than remain solid. This is the same principle that keeps Lake Vostok in Antarctica liquid despite sitting beneath approximately 4 kilometers of ice, sustained entirely by geothermal heat from below. Laughlin and Adams, writing in 2000, argued that a terrestrial road planet receiving negligible energy at its surface could sustain a subglacial liquid ocean if it had a thick enough ice layer. The ice acts as an insulator, slowing the loss of heat from the interior to space. The thicker the ice, the more effective the insulation, and the more easily the geothermal flux can maintain liquid conditions at the base of the ice sheet. This is not a distant or exotic scenario. We have a nearby example of exactly this kind of world in our own solar system. Europa is the 4th largest of Jupiter's moons, roughly the size of Earth's moon, and it is covered in a global shell of water ice. Beneath that ice shell, which is estimated to be somewhere between a few kilometers and perhaps 30 kilometers thick depending on location, scientists believe a saltwater ocean exists that may contain more than twice as much liquid water as all of Earth's oceans combined. The ocean is kept liquid by a combination of tidal heating, the gravitational flexing of Europa's interior as it orbits Jupiter in a slightly elliptical path, and, to a lesser extent, radiogenic heat from its rocky mantle below. Europa has never been warmed directly by the sun in any meaningful way. Jupiter receives about 25 times less solar energy per square meter than Earth does, and Europa orbits Jupiter at a distance that receives even less. What keeps Europa's ocean liquid is overwhelmingly internal energy, tidal and radiogenic. The sun is essentially irrelevant to Europa's interior thermal budget. If we move Europa to interstellar space, if we took it away from Jupiter's gravitational influence, and therefore from the tidal heating that currently dominates its energy budget, it would lose that tidal component. Its ocean would eventually freeze more deeply, but the radiogenic heat from its rocky interior would continue, and a sufficiently thick ice layer would continue to insulate what remains. Europa in deep interstellar space would be colder, more frozen, more hostile, but would not necessarily be entirely frozen solid, and not necessarily for billions of years. The same logic applies to any icy moon or water-rich rocky world that ends up as a rogue. The specific numbers depend on the object's mass, composition, water content, and the time elapsed since ejection. But the principle is robust. Internal heat plus an insulating ice layer can maintain liquid water in the dark. Enceladus, Saturn's small, bright moon, adds another dimension to this picture. Enceladus is tiny, only about 500 kilometers in diameter, smaller than many asteroids. By any prior intuition, a world this small should be geologically dead. It should have lost its internal heat long ago. But Enceladus has active geysers at its south pole, erupting plumes of water vapor, ice particles, and organic compounds into space. Beneath its icy surface is a global liquid ocean, confirmed by the Cassini spacecraft, in contact with a rocky seafloor. The heat driving all of this is tidal, the same gravitational flexing that warms Europa. But the critical point here is not the tidal component specifically. It is what the ocean contains. Cassini flew through the plumes of Enceladus and found, among many other things, molecular hydrogen, a chemical signature of hydrothermal reactions between liquid water and hot rock at the seafloor. It found silica nanoparticles, which form only when water circulates through rock at temperatures above 90 degrees Celsius. It found organic molecules of considerable complexity. In other words, Enceladus has hydrothermal vents at the bottom of its ocean, warm, chemically active environments where water interacts with rock, releasing energy and nutrients into surrounding liquid. Why does this matter for rogue planets? Because on Earth, hydrothermal vents at the bottom of the ocean are among the most productive ecosystems we know of. They exist in complete darkness, far below the reach of sunlight. The organisms that live there, bacteria, archaea, tube worms, crabs, shrimp, do not derive their energy from photosynthesis. They derive it from chemosynthesis, the use of chemical energy released by reactions between hot mineral-rich water and the cold ocean around it. No sunlight required. Deep-sea hydrothermal vents have played a major role in the development of life on Earth, providing a constant source of energy and nutrients for extremophilic organisms that form the basis of ecosystems in complete darkness. Some origin of life researchers have proposed that hydrothermal vents were not merely habitats for early life, but were the actual birthplace of life, the environments where the first self-replicating chemistry began. If that is true on Earth, if life can begin and sustain itself in the dark, heated only from below, dependent on chemistry rather than sunlight, then the question of whether rogue planets can support life is not as absurd as it might first appear. Let us now consider something that has recently emerged as perhaps the most promising thread in this entire line of research. When a planet is ejected from a solar system, it does not necessarily travel alone. Many planets have moons. Earth has one. Jupiter has almost 100. Saturn has more than 140. These moons orbit their planets due to gravity. And when a planet is gravitationally ejected from its system, the question of whether its moons come along depends on how violent and sudden the ejection was. 4 slow ejections, the kind caused by gradual gravitational perturbation over long timescales. There's actually a reasonable probability that moons remain bound to their planet. They have had time to adjust, in a sense, to the changing gravitational landscape. The planet leaves, and its moons, orbiting the planet rather than the star, leave with it. Simulations published in late 2025 indicate that moons orbiting planets ejected from their stars by supernovae can remain gravitationally bound to their planets and develop highly eccentric orbits. This eccentricity drives tidal heating, potentially sustaining subsurface liquid water for extended periods, even in interstellar space. This is a remarkable finding. When a moon orbits its planet in an elliptical rather than circular orbit, the gravitational force it experiences varies as it moves closer to and farther from the planet. The varying force flexes and compresses the moon's interior, generating heat through friction, tidal heating. The more elliptical the orbit, the stronger the tidal forces and the more heat generated. Research from the Excellence Cluster Origins at Ludwig Maximilian University of Munich and the Max Planck Institute for Extraterrestrial Physics found that moons orbiting free-floating planets may be able to maintain liquid water oceans for up to 4.3 billion years. According to the researchers, dense hydrogen atmospheres combined with tidal heating could keep these distant moons warm enough for life to potentially develop and evolve over immense stretches of time. For 0.3 billion years. That is roughly the age of the oldest confirmed life on Earth. Complex microbial life was present on our planet within the first billion years. Multicellular life emerged after roughly 2 billion years of microbial evolution. If rogue moons can maintain liquid water for 4.3 billion years, then the timescales required for biological complexity, at least the kind we are familiar with, are not out of reach. This does not mean life exists on rogue moons. It means the timescale argument, the objection that there simply is not enough time for life to develop, cannot be used to rule it out. Let us be careful here, because this is where the temptation toward wishful thinking is strongest. We do not know that life can arise without sunlight. We know that life can sustain itself without sunlight because we have found it doing so on Earth, in deep ocean vents and in Antarctic ice, and in the rock kilometers below the surface. But sustaining life is different from originating it. Whether abiogenesis, the emergence of self-replicating chemistry from non-living matter, requires specific conditions that rogue worlds may lack is a genuinely open question. The two most prominent scientific hypotheses for the origin of life on Earth are the hydrothermal vent hypothesis, which places the origin in deep-sea alkaline vents in the dark ocean, and the warm little pond hypothesis, which places it in shallow surface pools with access to sunlight and UV radiation. These two hypotheses are actively debated. Neither is established as fact. If the hydrothermal vent hypothesis is correct, then rogue worlds with subsurface oceans and active hydrothermal systems have, in principle, the conditions needed for abiogenesis. If the warm little pond hypothesis is correct, if UV radiation from a star plays a necessary role in driving the chemistry of early life, then rogue worlds will lack a key ingredient, and even the most thermally active subsurface ocean might never produce anything living. We do not know which hypothesis is right. Any scientist who tells you otherwise is not representing the current state of knowledge accurately. What we can say carefully and honestly is this: the conditions for life as we understand it, liquid water, chemical energy, a source of relevant organic chemistry, and sufficient time, are not, in principle, impossible on certain types of rogue planets or their moons. The question of whether those conditions are sufficient for life to actually arise is one that biology and chemistry have not yet answered even for Earth, let alone for worlds we have never visited and cannot currently observe in detail. There is one more piece of this picture that deserves its own moment: organic chemistry. Life on Earth is built from carbon-based molecules. The organic compounds that form proteins, nucleic acids, lipids, and carbohydrates are all combinations of carbon with hydrogen, nitrogen, oxygen, sulfur, and other elements. The assumption that life elsewhere would also be carbon-based is not arbitrary. Carbon is uniquely suited to forming the long, complex, stable molecular chains that information-based chemistry requires. But it is still an assumption. What we know is that organic chemistry is not rare in the universe. It is ubiquitous. The interstellar medium, the gas and dust that fills the space between stars, contains hundreds of identified organic molecules, including formaldehyde, methanol, acetic acid, and amino acids. Meteorites that have fallen to Earth contain complex organic compounds that formed in the early solar system without any biological input. Comets carry organic material. Asteroids carry it. A rogue planet that formed in a planetary system was, during its formation period, bombarded by comets and asteroids the same way Earth was. Those impactors delivered organic compounds to its surface. Whether those compounds survived the cooling of the surface, whether they found their way into a subsurface ocean through fractures in the ice, whether they had any role in driving chemistry toward biology in that ocean, all of this is unknown. But the organic inventory that life would need as a starting point was almost certainly delivered during the planet's early, warm period. The chemistry did not stop existing simply because the planet was ejected. Let us now bring these threads together into a single, coherent picture, not a definitive answer, but the most honest summary of where the science currently stands. A rogue planet of Earth-like mass, ejected from a solar system within the first few 100 million years of its existence, would carry the following assets into interstellar space. First, it would carry internal heat, primordial heat from its formation, and radiogenic heat from the decay of uranium, thorium, and potassium in its mantle. That heat would decline over billions of years, but would not disappear on any timescale currently relevant to our question. Second, if it is water-rich, it would carry a global reservoir of water, initially liquid, eventually frozen at the surface, but potentially liquid at depth if the geothermal flux and an insulating ice layer cooperate. Third, if it retains a hydrogen-rich atmosphere under the right pressure conditions, it might maintain surface temperatures above the freezing point of water. The Steppenwolf scenario. This is the most optimistic hypothesis and the most difficult to achieve, but it is physically possible. Fourth, if its seafloor is rocky and geothermally active, it can support hydrothermal vent systems in contact with the subsurface ocean, chemically reactive environments capable, in principle, of providing the energy and nutrient gradients that support life on Earth's ocean floor. Fifth, if it retained a moon during its ejection, that moon's tidal heating could supplement the radiogenic heat and extend the period of liquid water by potentially billions of years. And sixth, it carries whatever organic chemistry was deposited on its surface during its early life, the same raw material that, on Earth, eventually became the molecular machinery of biology. None of this proves that life exists on rogue planets. All of it together describes a world that is not, obviously, necessarily sterile. Some researchers have gone further, proposing that rocky rogue planets with subsurface liquid oceans could harbor unicellular organisms based on chemical, osmotic, thermal, or other energy sources, and have speculated that, given the theoretically predicted high number of rogue planets, they could serve as vectors for galactic panspermia, transferring life to other planetary systems. These are speculative scenarios, explicitly labeled as such by their authors. We mention them not as established science, but as illustrations of where the logic leads when you follow it without artificial stops. There is something quietly unsettling about the picture that emerges from all of this. We are accustomed to thinking of the habitable zone, the region around a star where liquid water can exist on a planetary surface, as a primary criterion for whether a world could support life. It is a useful concept. It is the basis of most exoplanet habitability research, and it produced the intuition, dominant for most of the history of astronomy, that life was only possible in the warm, well-lit neighborhoods of stars. But the deeper we look into our own solar system, the more that intuition erodes. Europa is outside the habitable zone. Enceladus is far outside it. Titan, Saturn's largest moon, with its lakes of liquid methane and complex organic chemistry, is further still. And now we are seriously discussing whether worlds with no star at all, worlds cast out of every habitable zone that ever existed, might still carry the conditions for life within their own internally heated interiors. The habitable zone, it seems, was always an incomplete picture, a useful shortcut, but a shortcut nonetheless. The universe's actual approach to habitability appears to be considerably broader and stranger than our initial models assumed. What this means for the question of life in the universe is not yet clear, but it means the question itself is more open than it was 20 years ago. Every time we look more carefully at what life actually requires, not what we assumed it required, but what it demonstrably, minimally requires, the list gets shorter and the set of possible environments gets larger. We are moving, slowly, toward a new way of thinking about what a habitable world is. Not a world in the right orbit around the right kind of star. Not a world with the right surface temperature and the right atmospheric composition visible from outside, but a world with liquid water somewhere, chemical energy somewhere, and enough time for chemistry to become complex. By that definition, rogue planets, at least some of them, under some conditions, qualify as candidates, not confirmed habitats, not proven homes of life, but candidates, worlds that cannot be crossed off the list on physical grounds alone. And given that there may be billions or trillions of them drifting through our galaxy right now, the implications of even a small fraction being habitable are staggering. That is a thought worth sitting with in the dark. In Part 3, we will turn to what comes next, both scientifically and philosophically. We will ask what it would mean if life did exist on a rogue planet. We will follow the thread of panspermia, the idea that life can travel between worlds and that rogue planets might be among its vehicles. We will look at what our telescopes are about to reveal and what that means for how we understand our own place in this vast, wandering galaxy. And we will ask, finally, the question that has been running quietly beneath everything we have discussed tonight. What does it mean that we live on a world with a star? That we're the lucky ones, the ones who got to stay, when the majority of worlds in the galaxy may have been cast out long before anyone could ask that question? We have spent 2 parts of this journey building a case, carefully, cautiously, without overreaching, that rogue planets may not be the dead, frozen nothings we once assumed them to be. We have seen that internal heat, radioactive decay, insulating ice, and in some cases the tidal flexing of a captured moon could in principle keep liquid water alive in the dark for billions of years. We have seen that the chemistry life requires, organic molecules, energy gradients, time, is not absent from these worlds simply because their stars are gone. Now we arrive at the question that has been waiting quietly beneath all of it. If a rogue planet could host life, even simple microbial chemosynthetic life, clinging to warmth at the bottom of a buried ocean, could that life ever leave? Could a world with no star, drifting through the emptiness between stars, actually carry something living from one part of the galaxy to another? This is the idea known as panspermia. And tonight, in this final part, we're going to look at it carefully, what it actually proposes, what evidence exists for and against it, and what role, if any, rogue planets might play in it. Let us start with the basic idea. Stripped of speculation, panspermia is a hypothesis that life, or the chemical precursors to life, can be transferred between celestial bodies, moving from one world to another, surviving the journey, and potentially seeding biology in a new location. It is an old idea. Versions of it go back over a century, to scientists like Swana Arrhenius, who proposed in the early 1900s that microbial spores could be propelled through space by the pressure of starlight alone. That specific mechanism, light pressure pushing spores between star systems, has not held up well under modern scrutiny. The radiation environment of interstellar space is far harsher than Arrhenius imagined, and unprotected organisms would almost certainly be destroyed by cosmic rays and ultraviolet radiation long before reaching another star. But the core idea did not disappear. It evolved. Modern discussions of panspermia generally fall into a few distinct categories, and it is worth separating them clearly because they carry very different levels of scientific support. The first is what scientists sometimes call lithopanspermia, the transfer of microorganisms inside rocks ejected from one planet's surface by an asteroid or comet impact, traveling through space and eventually landing on another world. This version has the strongest observational foundation of any panspermia hypothesis because we have direct evidence that the rock transfer part of the process actually happens. Meteorites found on Earth have been definitively traced to Mars, ejected from a Martian surface by ancient impacts, drifting through space for millions of years, and eventually falling to Earth. We have pieces of Mars in museum collections right now. The mechanism of transport is not hypothetical. It is documented. What remains unproven is the biological part. No meteorite from Mars has ever been confirmed to contain living organisms, fossilized organisms, or even unambiguous biosignatures. Some meteorites contain organic molecules. But as we discuss in Part 2, organic molecules are common throughout the solar system and do not by themselves indicate life. Laboratory experiments have shown that certain hardy microorganisms, particularly bacterial spores and some extremophiles, can survive extreme conditions of vacuum, radiation, and temperature for extended periods under controlled experimental conditions, including experiments conducted on the exterior of the International Space Station. But surviving controlled experiment in low Earth orbit for a period of months to a few years is a very different proposition from surviving an interstellar journey lasting millions or billions of years. This brings us to the second category, the idea that rogue planets themselves, not just rocks ejected from a planet's surface, but entire worlds, might serve as vehicles in this process. The reasoning goes something like this. If a rocky world with subsurface ocean is ejected from its system, and if that ocean harbors microbial life of the kind we discuss in Part 2, life sustained by internal heat and hydrothermal chemistry, then that life would not need to survive on the surface of the planet, exposed to the vacuum and radiation of interstellar space. It would be protected, potentially by kilometers of ice, for the entire duration of the planet's journey. The rogue planet, in this scenario, is not a spore drifting helplessly through the void. It is an ark, a sealed, insulated vessel, carrying its biosphere with it. Some researchers, and we want to be precise about the word some here, because this is genuinely a minority position within a field that is itself speculative, have proposed that if rogue planets are as numerous as current estimates suggest, and if even a small fraction of them harbor subsurface life, then the slow drift of these worlds to the galaxy over billions of years could, in principle, occasionally bring a rogue planet close enough to another star system that some exchange of material becomes possible. A close passage near a young system, combined with the kind of impact events that produced the Mars meteorites we mentioned earlier, could theoretically eject material from the rogue planet's crust material that might, in turn, carry organisms into the new system. We want to be extremely clear about the status of this idea. It is a hypothesis built on a chain of other hypotheses. It requires rogue planets to host life, itself unconfirmed. It requires that life to survive ejection events, unconfirmed. It requires close encounters between rogue planets and active star systems to be frequent enough to matter, which, given the vastness of interstellar distances, would require an extraordinarily long timescale even if rogue planets are as common as estimated. No evidence currently exists that this has ever happened. No evidence currently exists that it is even physically plausible at meaningful rates. It remains at every step a hypothesis, one that some researchers find worth exploring precisely because it follows logically from things we do know, even though none of the connecting steps have been demonstrated. What can be said with more confidence is something narrower and less dramatic, but still remarkable. Rogue planets demonstrate that the universe does not require a star to maintain the conditions life depends on, whether or not they ever transport life between systems. The mere possibility that they can sustain it quietly for billions of years in total isolation expands our sense of where life's address book might extend. Let us turn now to a question that brings this entire topic uncomfortably close to home. Could the Earth itself ever become a rogue planet? The honest answer is almost certainly not, at least not on any timescale that matters to us, or to any descendants we might have. Our solar system, as far as current models indicate, is dynamically stable on timescales of billions of years. The orbits of the planets are not perfectly fixed. There's ongoing research into long-term orbital dynamics suggesting that, over timescales of many billions of years, small gravitational interactions could in principle lead to instabilities in the inner solar system. But these are extremely long, extremely uncertain timescales, generally discussed in the context of many billions of years into future, well beyond the timescale on which the Sun itself will have already changed dramatically. The Sun is roughly 4.6 billion years old and is expected to remain in its current, relatively stable phase, known as the main sequence, for approximately another 5 billion years. After that, it will expand into a red giant, and the inner solar system, including Earth's current orbit, will be transformed in ways that have nothing to do with rogue planet ejection and everything to do with stellar evolution. In other words, long before any gravitational instability could plausibly eject Earth from the solar system, the Sun's own evolution will have already reshaped our neighborhood beyond recognition. The scenario that could eject Earth on a much shorter timescale, a close encounter with a passing star, is statistically possible but exceedingly unlikely. Stars in our part of the galaxy are separated by light years on average. Close stellar encounters, within a light year or so of the Sun, are estimated to occur only occasionally over millions of years, and an encounter close enough to actually disrupt Earth's orbit specifically would be far rarer still. It is not impossible in the way that, say, a perpetual motion machine is impossible, but it is the kind of event whose odds are measured against timescales many times longer than the current age of the universe. So Earth becoming a rogue planet is not a realistic concern. But the question is worth asking anyway, not because it is likely, but because of what it reveals when we ask it. If Earth were ejected, hypothetically, for the sake of the thought experiment, what would actually happen? In the days and weeks following such an event, very little would change immediately. Earth's atmosphere would not instantly freeze. The planet has enormous thermal inertia. The oceans alone store vast quantities of heat, and the atmosphere itself, while it would begin to cool, would do so gradually. Within months, however, without the sun's input, surface temperatures would begin to plummet. The water cycle would collapse. Within a few years, the oceans would begin freezing from the surface downward, though, as we discussed with Europa and Lake Vostok, the deep ocean, insulated by an increasingly thick ice shell, would remain liquid for a very long time, kept from freezing solid by Earth's own internal heat. The atmosphere itself would undergo a slow collapse. Water vapor would freeze out first, then carbon dioxide, and eventually, over a longer time scale, even nitrogen, the dominant component of our atmosphere, would begin to condense onto the frozen surface as the temperature continued to drop toward the background temperature of interstellar space. On the surface, almost nothing would survive. But Earth, it turns out, already has an answer to the scenario, one that exists right now, today, without any hypothetical ejection required. Kilometers beneath our feet, in rock formations isolated from the surface for millions of years, scientists have found living microbial communities, organisms that derive their energy not from sunlight, but from chemical reactions of the surrounding rock and water, sustained by Earth's own geothermal heat. This is sometimes called the deep biosphere, and by some estimates, it may contain a substantial fraction of all microbial life on Earth by sheer volume, even though it is entirely invisible from the surface and entirely independent of the sun. If Earth were somehow cast into interstellar space, the deep biosphere, life that already exists today, completely disconnected from sunlight, would very likely be the part of our planet's biology with the best chance of persisting. Not for comfort, not for any of the things we associate with being alive, but for sheer continuation in the dark, fed by the same radiogenic and primordial heat that we have spent this entire series discussing. It is a strange thought that the part of Earth's life best suited to survive the loss of the sun is a part of Earth's life that has, in a sense, never depended on the sun in the first place. It was already living the way a rogue planet's biosphere might live, quietly in the dark, power from below. This brings us, finally, to the instrument that will help turn much of what we have discussed from hypothesis toward measurement, the Nancy Grace Roman Space Telescope. We introduced Roman in Part 1, in the context of its planned microlensing survey, a survey expected to detect hundreds of rogue, Earth-mass planets through the gravitational lensing technique we described earlier. Roman is currently targeted for launch no earlier than late 2026, managed by NASA, and represents one of the most ambitious infrared survey telescopes ever built. Its wide field of view, roughly 100 times larger than that of the Hubble Space Telescope, while matching Hubble's image resolution, will allow it to monitor enormous numbers of stars simultaneously, which is precisely what microlensing surveys require. For the subject of this series, Roman's significance is twofold. First, as discussed, it should dramatically increase the known population of rogue planets, moving the field from a handful of confirmed detections toward what could be hundreds of new discoveries, providing a first real statistical picture of how common these worlds actually are. Second, and more speculatively, the data Roman collects may eventually help refine estimates of how many rogue planets are likely to be the right size, composition, and age to host the kind of subsurface oceans we have spent this series discussing. Roman will not be able to directly detect liquid water on a rogue planet. That level of detail is far beyond what any current or near-future telescope can achieve for objects with no light of their own. But by dramatically improving our senses of these worlds, their masses, their frequency, their distribution across the galaxy, Roman will narrow the uncertainty that currently surrounds nearly every number we have discussed in this series. In the years following Roman's launch, the rough estimates we have cited throughout the series, billions, trillions, a quadrillion, should begin to sharpen into something closer to an actual count. We will not know, even then, whether any of these worlds harbor life. That question may remain open for a very long time, perhaps permanently, given how difficult it is to study an object that emits no light and reflects almost none. But we will know, with much greater confidence, how many candidates exist. And given everything we have discussed about what those candidates might be capable of, that number alone will be worth knowing. We are nearing the end of this journey, and it seems right here at the close to step back from the physics, the heat flux, the tidal forces, the microlensing statistics, and sit for a moment with what all of it means. We began this series by calling rogue planets the most alone places in the universe. And in a literal physical sense, that description holds. No star, no system, no light from above except a faint, indifferent glow of distant points that provide no warmth at all. By any conventional measure, these are the most isolated objects we know of, more isolated than anything on Earth, more isolated than any human experience of solitude could meaningfully compare to. And yet, across this series, we have found something unexpected hiding inside that isolation. Heat that persists, chemistry that continues, oceans that, against every intuition built from a lifetime spent under a star, might still be liquid, might still be emotion, might still be doing whatever it is that liquid water does when it is in contact with warm rock and complex molecules in enough time. Isolation, it turns out, is not the same as emptiness. A rogue planet is alone, but it is not necessarily empty. It carries with it everything that was given during its formation: heat, water, chemistry, sometimes a moon, and it continues to be whatever it was quietly in the dark for as long as the physics allows. There's a way of thinking about this that extends beyond planets. Every one of us carries, in some sense, the heat of our own formation, the people, places, and experiences that shaped us before we were cast into whatever distance now separates us from them. And every one of us, at some point, moves through stretches of life that can feel like interstellar space. Cold, dark, apparently empty, with no external source of warmth in sight. The question a rogue planet quietly answers, does anything persist in a place like that? Is a question many people ask, in one form or another, about their own lives. The answer the universe seems to be giving cautiously through the physics we have spent the series exploring is yes, something can persist. Not because the darkness is secretly warm. It is not because isolation is secretly connection in disguise. It is not that either, but because what was built, the heat, the structure, the internal chemistry of a thing, does not simply vanish the moment the external light disappears. It continues on its own terms, according to its own internal processes, for far longer than the light was ever present in the first place. We do not know whether any rogue planet has ever produced, or will ever produce, anything we would recognize as life. We may never know. The distances are too vast, the objects too dark, and the timescales too long for certainty of that kind. But we know they are out there, billions of them, perhaps trillions, drifting individually through a galaxy that no longer remembers the stars that made them, carrying their oceans, their heat, their chemistry in silence, into a future with no audience and no end in sight. And somewhere among them, we cannot say how many, we cannot say where, it is at least possible that something in the dark beneath the ice, warmed from below by the same physics that warms the heart of our own planet, is quietly, slowly, continuing to exist. That is where we leave this story, not with an answer, with a possibility, carefully reasoned, honestly uncertain, and large enough to hold for a very long time.